Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we have the second session of the Moment Area Method. Last time, we had an easy example where you had a cantilever beam. And the easiest thing about the cantilever beam is that you have the at the fixed support, there is no rotation and there is no deflection. So we had a point to start from. Today we are going to look at a simply supported beam, and this beam has two concentrated loads acting on it, an 80 kilonewton at B, which is 2 meters from the left support, and a 40 kilonewton at C, which is 2 meters to the left of the right support. The problem asks you to find the slope at A, the slope at D, and the deflection at B, at the highest load. So we need to know how we are going to do that. Usually it's better to draw the elastic curve or just an idea how it's going to look like, because we will be using that later. We also need to find the reactions at the support, and we also need to draw the bending moment diagram. Once we have all these ingredients, we'll see how we are going to use them to find the slope and the deflection. So we can say roughly, I mean, it's not, accurate or anything. We are not to do any calculation for the elastic curve, but it's going to look something like that. Maybe, oops, something like that. Okay. Of course, it's going to, these forces will make it deflect like that. I still have a problem. I don't know the slope at any point on this beam, right? So how do we solve to find the deflection, the slopes and the deflection? One way to do that is to, that's how we are going to use it for all this would be very low. So, okay, let me redraw it in a different way. I will see why in a second. So that when we take the tangent at A, it doesn't go very low, so we won't have a space to draw the bending moment diagram and so on and so forth. So well, it's drawn just to give an idea. So here I'm gonna say here is the tangent at A, which means that this angle would be theta sub A, right? Notice theta sub A is a very small angle. And what do we know about small angles? We know as the limit of theta approaches 0, the angle in radian is the same as the sine is the same as the tangent, right? All of them would be the same. So we are going to call that T D with respect to A. T here is the deviation of the point or on the, so, okay, the deviation on the point on the elastic curve with respect to the tangent at A. Okay, so that is how, that's how deviated this point, the tangent from the point D on the elastic curve. On the elastic curve, we know there is no deflection whatsoever. So all of that is the deviation of D from the tangent at A. We call it T D sub A. But what is T D sub A? T D sub A is when we draw the bending moment diagram, if you take each part of the bending moment and multiplying by the centroid from D, that's where you are taking, D is the first letter. So it's the deviation of from D So you multiply each part of the bending moment diagram. If it's only one triangle, just multiply this triangle by how far the centroid from D is, which is 1/3 of the base. If it's more than that, you can break it into triangles and rectangles and do the work similarly. Okay, so that's how we are going to do the deviation. And then you say, but I wasn't looking at the deviation. I was looking at the slope. You say, wait a second. If I know this guy and I have the base as 8 meters, the tangent of A, which equals theta sub A in radians, would be that quantity that I calculated divided by 8 EI. Why EI? Because we said we are going to divide the bending moment diagram by EI. Here, if we assume EI is constant, so we are just getting the same shape. So let's find the reactions at the support to start the process. Okay, there's a way, by the way, there is a quick way to find the reactions, especially in a easy case like that. I'm going to break this into 40 and 40. So the first 40 and the first 40, they are symmetric. So they go to these supports as 40 kilonewton and 40 kilonewton. Okay, we are going to do it the regular way, but I'm saying you can do it quickly if that's not a test. You are doing some work, engineering work, and you want to find the reactions in a quick way. The remaining 40, so I took a 40 and 40 and make that 40 and 40. The other 40, do you see that it's located at a point that divides the beam into 2 and 6, meaning 1 to 3? Then the reaction will be the exact reciprocal of that. If this is 1 to 3, meaning out of 4 pieces, one is here, which is 2 meters, and 3 is here, which is 6 meters, then the reaction from that concentrated load will be divided 3 to 1, just the opposite. Okay? So 3/4 of the 40 will go here, and 1/4 of the 40 will go there. Which 40? Remember, we divided that into 40 and 40. So I get 40 and 40 from the first 40s, and then 30 and 10 from the other part. So basically, this would be 40 plus 30, or 70 kilonewton, and this would be 40 plus 10, which is 50 kilonewton. Again, I should redraw the free body diagram because I cannot try the reactions with the supports being inserted, but it's just, I'm trying to save time and space, okay? So basically, if you are solving, you have to solve it. And you can say, for example, I can take the summation of the moment about A and equate it to 0. Counterclockwise is positive. So the 80 produces a negative moment, so negative 80 times 2. The 40 also is producing negative 40 times 6. But the dy is producing a positive moment plus 8 dy equals 0. You can see I can simplify by 8. So if I simplify by 8, I get 5. If I simplify by 8, I get 10. When I move the dy to the other side, I get dy equals 10 plus 30 equals, did we say, no, that's a 2, not a 1, I'm sorry. So you get 20 plus 30 equals 50 kilonewton, positive meaning up, and then summation of the forces in the y equals 0, up is positive. I have AY minus 80 minus 40 plus 50 equals 0. So AY equals 70 kilonewton up. Again, same thing. I just wanted to show you a quick way when you have. Notice that if I only had 40 and 40, they will divide 40 and 40, right? This 40 will send 30 here and 10 here, and this will send 30 here and 10 there, so you get 40 and 40, which is common sense. If they are equally spaced from the center line, meaning they are symmetric, they will go as they are to the supports. Okay, now let's go to business. Let's draw the bending moment diagram, because that's the last thing we want to calculate. Bending moment diagram, I have 70 times 2 is 140. So if we go up, maybe if we say this is 100, this is 140, and 50 times 2 is 100. So if we go up 100, the bending moment diagram would look like that. So you can see I have two triangles and a trapezoid. I can divide the trapezoid into a triangle and rectangle, so it's much easier to calculate the centroids and stuff like that. So this is 100. If I say this is bending moment diagram divided by EI, so I can write here 100 kilonewton and here 140 kilonewton, and that's it. I have three triangles, so let's call them 1, 2, and 3. And I have one rectangle, so that's shape number 4. I'm going to say TD with respect to A. I'm going to take the area of each part and multiplying by how far it is from D. I'm taking the moment about point D. So I'm going to say for the first triangle, it's 1/2 base times height. And the distance from the centroid, I know it's 1/3 of the base. And if the base is 2, so that distance is 2/3. Plus 4 plus 2, which is 6. 6 is 18/3. 18 plus 2 is 20/3. Plus, this rectangle is 1/2 times 4, the base, times 40, because this is 100, this is 140, so times 4 times 40, and the centroid is here. If this distance is 4, it's 4/3 from here, or 12/3 from there. 2 is 6/3, so I'm sorry, I said 12/3, yeah. 2, and the centroid, and that distance, what did I do? We said, no, I'm sorry, this is 8/3. Why did I say 12? 12 is the total. I was calculating 4 times 3, and I wrote the total. Okay, so 8/3 plus 2, and 2 is 6/3. 8/3 plus 6/3 is 14/3. Plus, the third triangle has a base of 2, a height of 100, and the centroid is 2/3 of the base. If the base is 2, that distance is 4/3. So times 4/3. Plus a rectangle of base 4, height 100, and the distance from D is half the base, which is 2 plus 2 is 4. And then you can use the calculator to find that. 1/2 and 4 would be 2, 1/2 and 1/2 cancel, so I get 14 times 2 is 28, so this is 2800 over 3. Notice here is EI, you have to multiply or divide. Here I didn't do it because I said this is scaled down by the factor of EI. Plus, this is 56,560 times 2 is 1120 over 3. And here you get 400 over 3 plus 1600. So, okay, we can do a calculator. We can add them up and divide, but 2800 plus 1120 plus 400 divided by 3 plus 1600. It's 3040, 3040. Which means TD with respect to A is 3040 divided by EI. Nice. But we said theta sub A is basically TDA divided by 8. So it's TDA divided by 8 equals. So I'm going to divide this by 8. I get 380. The only thing is that this number is negative. Why? Because the rotation is clockwise. So I would say negative 380 over EI. Now, if you are given EI, like for example, 8 times 10 to the 6 or something, you divide that and you multiply it by 1,000 to make it in millimeter. Let's assume, just to get a rough idea. So assuming it's 8 million E times I, okay? So I would say this number, it doesn't matter the negative, divided by 8 million, but I'm going to multiply by 1,000. So by 8,000, it would be 0.04 millimeters. It's negligible because these are very, just too concentrated load. It's not distributed load. It's not. Anyway, so that's theta sub A. Now, how do I find theta sub B? Someone would say, yeah, I can draw a slope here, repeat the work, but instead of taking the centroid from D, I take it from A and solve. Yeah, we can do it. Let's do it. But there is a better way. If you understood what we said last time, there is a better way. Okay, so here is TA with respect to D. I can repeat the calculations. That's not an efficient way, by the way, to do it. We'll see what's the efficient way. Well, 1/2 times 2 times 140 stays the same. But now this distance is 4/3, right? If this is 2/3, then this is 4/3. Notice you can see that these two centroids must add up to 8, right? Because A and D are 8 apart. So there is no reason to calculate it from here. I'm going to subtract this from 8, or 24/3. So plus 2 times 40 times, so we said 2 times 40 is 80 times 10/3. Oh, did we say? Yeah. Okay. So again, here is this distance, 8/3. So this is, I'm sorry, we're taking it from here. So this is 4/3 and 2, which is 6/3. 6 and 10. 6 and 4 is 10. Or we can subtract that from 8, which is 24/3. So if this is 14, the other must be 10/3, right? This one, I no longer need to calculate it. It's 100 times 20/3. Why 20/3? Because this is 4. Plus 4 times 100. Well, if this is 4, the other is also 4, right? Because they add up to 8. And we know it's exactly in the middle, so it's equidistant from these two. Again, the 2 and the 2. So this would be 560 over 3 plus 800 over 3 plus 2,000 over 3 plus 1,600. It should be the same. I should get the same result, right? Not the same result. I mean, there's some. Okay, we'll see that. There's some will be something. So I'm going to say 560 plus 8 plus 800 plus 2,000 divided by 3 plus 1,600. I get 2720. 2720 over EI. Oh, no, I already multiplied by EI. It means theta sub D is, divide that by 8, and you get 340 over EI. This is positive 340, right? Because it's rotating counterclockwise. It would have been much easier if we say, remember what we said, the slope of one point compared to a slope of another point that I already know equals the area of the bending moment diagram between them divided by EI. What is the area? The area, notice it's without multiplying. So this is 140. This is 80. This is 100. And this is 400, right? 400, 500, 640, 720. So the total area equals 720 over EI. Now, if I added 720 to theta sub A, I will get 340. These two numbers as an absolute value. And if I subtract this from that, because notice this is positive and that is negative, I will get negative 380. So once you know one of them, you can easily find the slope at any other point. I can find the slope at B by simply adding 140 over EI to this. So I get negative 240 over EI. I already found it. If I want this, I can either add these three to that or subtract 100 from that. So I get 240 over EI. What do you think? Make sense? Okay. So here we said, once I find TD with respect to A or TA with respect to D, I say that this whole thing is just deviation from the tangent. But if I calculate it here, for example, no, it's not a deviation from because the deviation from the tangent is only this part. So what is the rest? The rest is the deflection. Which means if I want to find the deflection at B, I have two ways, a shortcut and a slightly longer way. Of course, I can start from D with this thing and calculate TB with respect to D, which doesn't make sense because I have 1, 2, 3 areas, or start from A and just use one area. In fact, just to show you that it really doesn't matter computationally, I will do both. One of them is more efficient than the other, definitely, but it really doesn't matter. Let's look at this deviation. You see the point of intersection of a line going below 80 and the elastic curve is delta B. The other part is T, deviation of B with respect to the elastic curve drawn from D. So I need to draw or to calculate TB with respect to D. Okay, TB with respect to D, meaning I'm going to take these three areas and multiply each one by the distance from its centroid to point B. So if I start with area 2, it's 1/2 times 4 times 40 times the centroid from here, which is 4/3. It's written to me here. Plus 1/2 times 2 times 100. And if this is 4/3, this is 2/3. 2/3 plus 4, which is 12/3, is 14/3. And finally, plus 4 times 100, which is the height, times 2 over EI. So let's say EI times that equals 2, 8, 320 over 3 plus 1400 over 3 plus 800, or I can write it 2400 over 3, so make everything over 3. Now when I add those, I get 38, 4120, right? 4120 over 3, meaning the TB with respect to D is 4120 over 3, so which is this distance. But what is the total distance? I say, how do I know? No, you know. What is the total distance? The total distance, if this is theta sub d, which we found here, if you multiply it by 6, you get this total height, right? So 6 theta sub b equals TB with respect to D plus delta B. See how easy it is now. So I'm going to say delta B equals 6 times 340 over EI. But notice this is below, so it has to be negative. Of course, deflection negative meaning going down. So you can add the negative sign at the end. But then you have to subtract TBD from that. So let's leave the negative sign at the end. Or you can say negative, and then you take 6 times 340 over EI minus TBD, which is 4120 over 3 EI equals. Now, we can say, notice this is a number and this is over 3. So I can take 3EI as a common denominator, multiply 6. That doesn't make sense, does it? Yeah, maybe. 6 times 3 times 340 minus 4120 equals 2000 over 3 EI. In fact, it's negative because it's going down, but that's the deviation or the deflection at B. Someone else would say, why do I use all of that? Couldn't I just look at it from the left-hand side? And if I look at from the left-hand side, I will get 2 theta sub A equals T B with respect to A plus deflection of B. But the TB with respect to A is easier because it's only one triangle. I want to take the integral of, the product of the area of this triangle times its distance from the centroid. In fact, I see it right there. It's 280 over 3. Is that just that? So I can say, again, there is no reason to say 1/2 times 140 times 2 times 2/3, right? It's simply 280 over 3. Now, theta sub A was negative 380. So when I multiply it by 2, I get negative 760 over EI equals 280 over 3 EI. Again, I didn't write the EI here, plus delta B. So delta B equals negative. I'm going to multiply this by 3 and add it to that. Notice both would be negative when I move this to the other side. So it's negative over 3 EI. Multiply 760 times 3 and then add 280. Oops. No, I subtract 280. Again, yeah, the only reason is that now we already know that the deviation is negative, but you added already the negative. So you're simply going to say 760 times 3 minus 280. I'm sorry, this is not correct. And you get 2000 over 3. Yeah, you already know that this is negative, but it's the slope itself as an absolute value. It's a slope, and you are saying that this distance, so you cannot say this distance is negative, right? So that distance from here, really from this point to that point, is TB with respect to A plus delta B. TB with respect to A is much smaller than TB B with respect to D, which is much higher, right? And basically, I think that's it, right? There is nothing else. We found the deflection at B in 2 different ways, and both of them give me the same result. And basically, we found theta sub A and theta sub D. Next time, we are going to take a case, maybe more complicated like than that, like has more loads. And then what we are going to do is to find also the slopes and the deviation. And then I will ask you, where is the maximum deflection and what is its value? So we'll see how we do that. And I think that will be enough for the moment area method, unless we see something interesting. Again, as usual, thank you very much for your time. I hope you enjoyed this session. If you have any questions or comments, please let me know. Otherwise, I wish you all the best and hope to see you soon. Bye.